Welcome to lesson 3.1.2. Today we're going to do a famous 8th grade CPM problem called John's Giant Redwood. Oh, how I wish I had John's Giant Redwood when I was a kid, because this is just a better way to learn about tables, graphs, rules. Such a good lesson. So here we go. John's Giant Redwood. Problem 3-10, you have your notebook open to lesson 3.1.2, and we'll go ahead and dive right in. John found the data in the table below about his favorite redwood tree. If you've been here at Palermo School, you know what a redwood tree looks like, because there is a really tall redwood tree by the cafeteria. It is ages old. I have been to the top of that redwood tree, and it's a fun one to climb. He wondered if he could use it to predict the height of the tree at other points in time. So notice he only collected information in year 3, year 4, and year 5. But he wanted to know if he could collect data in other years. Be ready to share and justify your answers with the class. So you will notice on your paper, you have an extended table. You have 2, 1, 0. You also, I believe, have 6, and you might even want to draw in 7. Okay. Now, here's what we're going to do. We're going to look at this table, and you are going to fill information in. So here we go. Letter A. You'll notice there are 4 lines down at the bottom for us to answer these 4 questions down at the bottom. Letter A. How much did the tree grow each year? Now this is talking height. How much did it grow? Okay, so let's look at the numbers. 17 to 21. Well, that's from 17, 18, 19, 20, 21. It grew 4 years. Let's see if it repeated itself. 21 to 25, yep, it grew 4. So let's go ahead and write letter A. John's redwood tree grew 4 feet each year. John's redwood tree grew 4 feet each year. Problem letter B. How tall was the tree 2 years after it was planted? And this is going to be really helpful if you go ahead and complete the table. See, if you have a table that comes out here, and you know 6 and you know 7, then you can use the growth of 4 to go ahead and grow it up. 25 plus 4 is 29. 29 plus 4 is 33. That's growing the table up. Now, if you know that it grows by 4, added 4 each time, how would we work our way backwards? Well, that's subtraction. So I subtract by 4 to get 13, subtract 4 to get 9, and we subtract 4 to get 5. That's what a completed table would look like. Now let's answer the question. How tall was the tree 2 years after it was planted? So you're right. After 2 years, it was 13 feet tall. After 7 years, it was 33 feet tall. How do you know? You use the growth to complete the table. That's what we did. We used the growth of 4 to complete the table. Other people said, I added 4 or I subtracted 4. That's how you figure this out. Go ahead and write your answer for problem letter B. Pause if you need to. How tall was the tree the year it was planted? Now, is that 1? How tall was it after 1 year? No, not 1 year. How tall was it the year it was planted? That's 0. How tall is the tree? Well, you should see that number in your table. The number was 5. Okay, and when we are looking at this table, we can see that It's like John went to Home Depot, bought a redwood tree, and it already had height. It's not like he bought a seed. No, he bought a tree. He brought the tree home. I want this tree to go right here, and it was already 5 feet tall. Okay? John's giant redwood was 5 feet tall when it was planted. Now, estimate the height of the tree 50 years after it was planted. There's a couple ways to make a prediction. You could count this out all the way up to 50. You could count that out and count this out. But I want you to make a prediction. I think John's tree will be blank feet after 50 years. Go ahead and make a prediction. Pause the video. Make a prediction. All right. Let's go ahead and talk about the graph. Okay? So on your paper, you'll notice that we have a graph. And if I go ahead and complete this table, 5, 9, 13, and 29. Okay? So here's what we're going to do. We're going to go ahead and plot the points. Down here, you have years. Go ahead and label years. On this side, we have feet. This is also the height of the tree in feet. You could label it that. And what we're going to do is we are going to plot these points. Here we have 0, 2, 4, 6, 8, 10, 12. Just notice how it's counting, okay? So I'm going to go ahead and graph my points. 0, 5, 1, 9, 2, 13, 3, 17, 4, 21, and 5, 25. Go ahead and plot your points. Pause the video if you need to. Okay, question. What does this graph look like? Well, looks like a straight line to me. Is it proportional? Because it's a straight line, is it proportional? And the answer is no, because it does not start at 0, so no. On the back side of your paper, you'll notice problem 3-11A is at the top of the next page. You need to write the answer for 3-11A. Here it is. Our graph is a straight line, comma, but it is not proportional, period. Our graph is a straight line, comma, but it is not proportional. Okay? Problem letter B. Does it make sense to draw the line? Does it make sense to draw a line? And some of you might say, of course it does, Mr. McCoy. We always draw lines, right? Like that's the point of graphing. We draw a line, right? Well, yeah, that makes sense, but why are we drawing the line? And the real question is, what does a graph represent? Is this graph only information at the dots? And the answer is no. This graph represents all the numbers. It represents all the numbers, whether they are whole numbers or they are in between numbers. For example, here's what I mean. Can this tree be half a year old? Can it be a half number? It's not a dot. Can it be a half number? And the answer is yes. After half a year, the tree was 7 feet tall, right? We can use the graph to represent any point of data on this graph. So it does make sense to graph this line because there's information between the dots. Let's go ahead and write that down for problem 3-11B. We drew a line connecting the dots because there is information between the dots. We drew a line to connect the dots because there is information between the dots. Question letter C. How tall was the tree a year and a half after it was planted. This was on the Chapter 2 test. And you go to 1.5 years, you go to the line, and then you go over. How tall was the tree 1.5 years after it was planted? You respond with, after 1.5 years, the tree was blank feet tall. Question letter D. And if I'm going too fast, you should be pausing the video. D. Can you use your graph to predict the height of a redwood tree 20 years after it was planted? Of course, Mr. McCoy. Let's go ahead and find the number 20 years. 1 year, 2 year, 3 year, 4 year, 5 year, 6 year. Wait a second. I can't find 20 years. Can I use this graph? A graph? Sure. Can I use this graph to do 20 years? No. Why? It's not big enough. So let's write D. We cannot predict 20 years using this graph because it's too small. We cannot use this graph to predict 20 years because it is too small. Pause it if you need to. Now, problem letter A, 312A, says find John's table on your resource page and include the height in year 0, year 1, year 2, and 6th year. So what I want you to do in 312A is write the word done, because it's done. We did that. We did that as a part of the beginning. Now, here's what I want you to do for B. If you have not already done so, use the ideas that we talked about on Monday on a table, lesson 311. Okay, the previous lesson, 311. When you are looking at a table, there are two ways to find the answer. You are either guessing and checking. What do you do to the top number to land on the bottom number? That's one method. The other method is, what do you do to 0 to end up with 5? Remember, multiplication and division have no power over 0. So you know that part of the rule is going to be add 5. You know that. You know that it's add 5. Because 0 plus 5 is 5. Remember, numbers always begin at 0. Tables begin at 0. When we're doing this, we need to be able to find that 0 because it's the key to unlocking the rule. Now, if I know part of the rule is plus 5, I can pick any of these other numbers. Okay, I'm going to pick 25. 25 take away 5. Notice, I'm going to use the opposite here to find how to work my way back. Okay, so 25 minus 5 is 20. So 5 times what is 20? 5 times 4 is 20. Now notice I can check that. 4 times 4 is 16 plus 5 is 21. Now I find it curious, Mr. McCoy, that the pattern was add 4 each time, and that number 4 is also in there. If you remember back to 3rd grade when we taught you multiplication, multiplication is repeated addition. Repeat adding 4, repeat adding 4, repeat adding 4 is really just multiplication. So, our last step. Let's check your prediction. In problem 310D, you estimated the height of John's giant redwood in 50 years. Let's go ahead and check our answer. 50, using the rule, times 4 plus 5 is, well, 5 times 4 is 20, so 50 times 4 is 200. 200 plus 5, we should estimate John's giant redwood to be 205 feet tall. Okay. Now we are developing ideas about tables, graphs, rules. We're trying to make all those connections. And John's Giant Redwood is a great example of how to create those interconnected points. And we're going to continue to dive into this throughout chapter 3. Thanks for tuning in to today's lesson and doing your job as we continue to learn about rules, tables, and graphs. We'll see you next time.